We are continuing looking at graphing rational functions. We talked about how to find vertical asymptotes. So recall those are values which set our denominator equal to 0, but also doesn't set our numerator equal to 0. If it sets our numerator also equal to 0, then we either have a hole there or it's a vertical asymptote. It depends on the multiplicity. The multiplicity of the denominator is higher, it's a vertical asymptote. If we cancel out all of our factors, then it's going to be a hole. We also looked at talking about horizontal asymptotes, horizontal asymptote and oblique asymptotes. And oblique asymptotes are also called slant asymptotes. Depends on the degree of the numerator and denominator. And so we're going to look at this example in front of us. H of x is equal to x squared plus 4. All over the denominator, which is x to the 4th minus 1. And so let's go through graphing this rational function using what we have learned in the previous lecture. So we want to graph this. We want to find our asymptotes. It will be helpful if we can find intercepts if they exist. And so let's look at our vertical asymptotes. So looking at vertical asymptotes, it's helpful if we can factor both the numerator and denominator if possible. So I'm looking at my denominator, and down there in my denominator, I noticed that that's actually a difference of squares. X to the 4th minus 1, I can factor. So I'm going to rewrite my numerator, x squared plus 4. That does not factor because that is not a difference of squares. That's a sum of two squares. And then x to the 4th minus 1, I notice I can factor this as x squared minus 1 all times x squared plus 1, which factors a little bit further. So I'm going to rewrite my numerator, x squared plus 4, all over. So this factor of x squared minus 1 is another difference of squares. So let's factor that. That can be factored as x minus 1, x plus 1. And then we have the factor still of x squared plus 1, a sum of two squares. It does not break down. It's an irreducible quadratic factor, which we'll talk about more in a couple sections. And so now we've broken down our function h of x and factored where we could. And now looking at this, I noticed that there are values which set my denominator equal to 0, but not also my numerator. And so I want to look at where these values are equal to 0. And these are values which are not in our domain of our function, but these are values which we're going to have vertical asymptotes. And so I'm looking at when is my x minus 1 equal to 0? Well, x minus 1 is equal to 0 when x is 1. And x plus 1 is equal to 0 when we have x is negative 1. So we have two vertical asymptotes. We can call it VA. And our vertical asymptotes were x equals 1 and x equals negative 1. So be careful there. It's not just equals 1 and negative 1. Those are equations. They're vertical lines. Vertical lines are in the form of x equals some number. Now let's go through and find our horizontal asymptote or oblique asymptote. So that has to deal with the degree of our numerator and denominator, and we're going to compare those, and depending on the comparison of the degree of the numerator and denominator, depends on if we have a horizontal asymptote or not. And so looking at the degree of my numerator, which is the highest exponent of that polynomial, that is a degree 2 in the numerator. And looking at the degree of my denominator, the highest exponent is a 4, so that's degree 4. If the degree of the denominator is larger, recall we have a horizontal asymptote, and that horizontal asymptote is going to occur at y equals 0. So we have a horizontal asymptote, HA, at y equals 0. And again, this is because the degree of the denominator is larger than the degree of the numerator. Okay, so we found our vertical asymptotes and we found our horizontal asymptote. If it has a horizontal asymptote, it doesn't have an oblique asymptote. Now let's look at finding our intercepts of our rational function. And so finding our intercepts, we know that our intercepts occur depending on if x is 0 or y is 0. And so to find our x-intercept, we're going to let our y value equal 0 and solve for x. Or in this case, we're going to let h of x equal 0 and solve for x. And so doing that, we have 0 is equal to x squared plus 4 all over x to the 4th minus 1. So recall we talked about when we're looking for our x-intercepts of a rational function, really we're only looking at where our numerator is equal to 0. Because if we went through and solved this like we were solving rational functions before, we cleared our fractions by multiplying both sides by our common denominator. And when we both multiply both sides of our common denominator by our common denominator, 0 times anything is 0. And so this is going to give us back 0 equals, and then our denominator cancels on the other side, just leaving us with our numerator x squared plus 4. So a couple ways we can go through and solve this quadratic equation. We can try to factor it. We can use the square root method, or we can use the quadratic formula. So looking at the form that I have this quadratic equation, I would probably use the square root method. But any of those cases I just said will give us the same result. And so I would isolate my x squared here because I just have a term with x squared and I don't have any other terms with x in it. And so I would subtract 4 on both sides. And doing so, I would get my x squared is equal to -4. Taking the square root of both sides. So remember, when we take the square root of both sides of an equation, we need to put plus or minus in front of one side so that we get all of the solutions. And so the square root of x squared is x is equal to plus or minus. So recall that the square root of a negative number is not a real number. They were an imaginary number. And so this would give us plus or minus 2i. And since these are imaginary numbers, are solutions, this tells me that it's not going to cross the x-axis. So we don't have any x-intercepts for this problem. So looking for our y-intercept, that's always the easier case of the two. So for the y-intercept, we're going to let x equal 0 and solve for y. So we're going to go in here, wherever we see an x, we're going to go in and we're going to drop in 0. And so we have x squared, so 0 squared, plus 4, all over, I have x to the 4th, so it's going to be 0 raised to the 4th minus 1. So simplifying this, we get this is equal to 4 over -1, which is -4. So we have a y-intercept when x is 0, y is -4. So going through what we just did, we only found one point on our graph. So once we found our asymptotes and we found our intercepts, if they exist, then we want to go and start graphing our function. And we're going to start graphing our function by going through and plotting our asymptotes by using dotted lines and plotting our intercepts. And so doing so, we had, again, horizontal or vertical asymptotes, I mean, x equals -1. And x equals +1. We had a horizontal asymptote at the x-axis, y equals 0. And we had a point at 0, -4. Okay, so just by knowing where my vertical asymptotes are, knowing that I'm not going to cross my x-axis, and knowing that I have a point between -1 and 1 at 0, -4, I know that somehow my graph in between this -1 and 1 is going to be hugging the vertical asymptote on the left of or on the right of -1, and on the left a +1. Because I can't turn around and cross that x-axis because I know again that there's no x-intercept. And so I know that it's some sort of shape in here. It might not be a parabola shape. It might, extend above and then come back down. I'm not exactly sure. And without techniques and tools from calculus or a graphing utility, I wouldn't know that. I could get a little bit better of an estimate by plotting a couple points in between -1 and 1, other than x equals 0. But for now, I have kind of a general shape of what's going on in there. Okay. So now let's go see what's happening on the other side of x equals -1. Again, by knowing where my asymptotes are, I can kind of tell what my graph is going to look like. I have two case scenarios that it could look like here on the left-hand side of x equals -1. I could have something up here in the third quadrant, or second quadrant, which looks like this. Or I could have something down here in the third quadrant that's going to look something like this. I won't know if it's above the x-axis or below the x-axis until I plot at one point. So let's do that. The same idea for on the other side of x equals 1. I'm either going to have my graph above the x-axis in that first quadrant, which was going to look something like this because of where my asymptote is, or I'm going to have something down here below the x-axis in my fourth quadrant that would look like this. But again, I don't know until I plot one point to see if I'm above or below the x-axis. And so I want to choose a point to the left of x equals -1. So something smaller than -1. So how about -2? So let's go back up, and in our original function, let's plug in -2 wherever we see an x. And so doing so, I have an x squared, so -2 squared plus 4, all over, I have x to the 4th, so -2 raised to the 4th, minus 1. So -2 quantity squared is 4, and 4 plus 4 gives me 8 in the numerator. Down in the denominator, I have -2 to the 4th. So -2 times -2 is 4, times -2 is -8, times -2 is positive 16. So -2 to the 4th is positive 16 minus our 1 gives us 15. So I notice this is a positive number at -2. It's less than 1. That's a little more than a half. And I see that because double 8, I get 16. And my denominator's 15. So a little more than a half. So just kind of estimate what you have there. So again, because this is above the x-axis, I know then what the shape is going to look like on the left of that vertical asymptote. So recall, we can never cross a vertical asymptote, but it's possible to cross a horizontal. And we'll test to see if this crosses the horizontal. Oh, actually, no, it doesn't cross the horizontal, because if it crossed this horizontal axis, we would have had an x-intercept. So it doesn't cross the horizontal in this case. So technically, I could be using information, knowing actually that this is, test to see if this is even or odd. And the reason why we would want to know if a function is even or odd, if it was an even function. So recall, to be an even function, if we plugged in -x wherever we saw an x, it would give us back our original function f of x. And if it was an even function, then the graph was symmetrical across this x-axis. So I actually see that h of x, if I plugged in -x wherever I saw an x and f of, or h of x, I'm going to get back my original function, because if I square my -x, it's the same thing as x squared plus 4. And if I raise -x to the 4th power and subtract 1, I'm still getting the same thing, x to the 4th minus 1. So without having to plot another point, I know that since I know -2 and 8/15 is a point, then I know that because it's even, then change the sign of my x value to, and the y value stays the same, 8/15 is also a point. And so I'm above the x-axis. I'm in the first quadrant when x is bigger than 1. I have a graph that looks similar to this. And so we get a general sketch of what our graph looks like by knowing where our asymptotes are and plotting additional points. So looking at one more example, we have here f of x is equal to 2x plus 9 over x cubed, and we want to graph this. So let's first start by rewriting this as a single fraction. So let's rewrite f of x. And so doing that, I need a common denominator. I notice that this 2 over x, or this 2x is over 1. And so our common denominator here is x cubed. And so we're going to multiply both our numerator and denominator here by x cubed. So if I do this, I get f of x is equal to 2x times x cubed is 2x to the fourth plus 9 all over x cubed. So looking at this, we want to find our asymptotes if they exist. Looking at this, I cannot factor either the numerator or the denominator. So to find my vertical asymptotes, we're looking at values which set our denominator equal to 0, but not also our numerator. Well, x cubed is equal to 0 if we took the cubed root of both sides to get x by itself and get rid of the cubed. We would get x is equal to the cubed root of 0, which is 0. So x is equal to 0 is our vertical asymptote. Looking for our horizontal asymptote, and that has to deal with the degree of the numerator denominator. So I have a degree 4 in the numerator. I have a degree 3 in the denominator. The degree in my numerator is larger. That means there's no horizontal asymptote. So if the degree of the numerator is larger, then it's going to have an oblique asymptote. Your book only says it has one if it's only one more. Degree is one larger than the denominator. And this is the case where it's one more. So just be aware of that when you're doing your homework, because they ask you while you're going through your homework, does it have a horizontal asymptote? If so, does it have an oblique asymptote or not? And so if your degree of your numerator is more than one larger than the denominator, then for your textbook and when you're doing the homework, you're going to tell it, no, it doesn't have one. Okay, so horizontal asymptote, no horizontal asymptote because the degree of the numerator is larger. So for our oblique asymptote, we're going to look at long division. And so we're going to take our denominator, x cubed, and we're going to divide it into our numerator, 2x to the fourth plus 9. So while you're doing this, you're thinking to yourself, what can I multiply x cubed by to get this first term down here underneath my division symbol, 2x to the fourth? Well, x cubed times 2x gives me back 2x to the fourth. And so let's multiply 2x by this x cubed. And so doing so, we get 2x to the fourth. We end up subtracting that off. And when we subtract that off, we get 0. Let's bring down our next number. And 9 minus 0 is 9. So I'm done. 9 is my remainder. And if I look at this, I have y is equal to 2x plus my remainder, 9, all over my divisor, x cubed. The thing is, as x tends to positive or negative infinity, 9 over something that's getting so huge or so huge, 9 over a huge number is going to 0. And so as x goes to positive or negative infinity, this piece of our remainder over divisor is always going to go to 0. And so we have an oblique asymptote at y equals 2x. Now looking for intercepts. So if I'm looking for my x-intercept, I'm going to let my y value equal 0. And so I have 0 is equal to, I'm going to do it to my rational function I found, 2x to the 4th plus 9 over x cubed. Multiply both sides by x cubed times 0 is 0. So I have 0 here is equal to 2x to the 4th plus 9. X cubed times that 2x to the 4th plus 9 all over x cubed. The x cubes cancel. I notice here I'm going to get an imaginary number, because if I subtract 9 on both sides and divide by 2, I end up getting my x to the 4th is equal to negative 9 divided by 2. Take the 4th root of both sides. I can't have a negative underneath an even powered radical. It's an imaginary number. So I can see that this is not real. So I have no x-intercept. If though I go in here and I plug in a 0 wherever I see an x, well, let's actually go back and talk about it with a real function, or not the real function. I guess they're both the real functions. Notice if I plug in 0 and for x here, to find my y-intercept, I would get 2 times 0 plus 9 all over 0 cubed. And I can't divide by 0. I have 0 in my denominator when I'm looking at the original piece. I guess I would get it also if I plugged it into the single rational function that we wrote it as. And so this is not possible. This is undefined, doesn't not exist. And so 0 is not in our domain. So there's going to be no y-intercept. Okay, so plotting what we have. And I guess we could have saw that by looking at that vertical asymptote. We can't cross a vertical asymptote, and our vertical asymptote was our y-axis. So that's another way that we could have showed that there was no y-intercept in this case. So we had a vertical asymptote on our y-axis, and we have a slant asymptote or oblique asymptote at y equals 2x. So it's a linear equation, and it's in the form y equals mx plus b. Technically, I would have a point at 0, 0 when I'm plotting this graph, but it's not part of our graph. I would rise, my slope is 2 over 1, so I would rise 2 and go over 1. rise another 2 and go over 1, or you can plot points. I could fall 2 from my origin and go over 1. And so looking at that, I have my oblique asymptote here. So we're never crossing our axes. And so we're either going to be completely above the x-axis or completely below the x-axis on either side of our vertical asymptote. And the only way I would know that is if I went in there and I plotted a point. And so we want to look at least 1 point on the left-hand side of x equals 0 and at least 1 point on the right-hand side of x equals 0. And I'm kind of looking at this to see, would I have an even or odd function? Because if I have an even or odd function, if I know 1 point, I would know another point. And so just again, to kind of review what we've talked about in the past in this course, let's test to see, is f of x even or odd? So if I go in there and I plug in negative x, wherever I see an x, I'm going to plug it into the single fraction. I would have 2 negative x raised to the 4th power. That when I multiply out negative x 4 times is positive x to the 4th. So I would get back 2x to the 4th plus 9 in the numerator all over. And if I plug in negative x into the denominator, negative x quantity cubed gives me back negative x cubed. So this does not equal our original function. So it's not an even function. And if I look at negative f of x, so multiplying my whole equation by negative 1, I would have negative of x to the 4th plus 9 all over x cubed, which looks like it's the exact same thing as f of negative x. I can technically take this negative that's down here in my numerator and I can bring it and just put it in front of the whole function. It's the same thing. And so since that's the same thing, this is equal to f of negative x. So f of x is an odd function. So odd functions, recall, were functions that were symmetrical across the origin. And another thing we knew about odd functions, if xy was a point on our graph, then we had another point on our graph, which was negative x, negative y. So now when we go in here and we plot in one of our points, so if we plugged in negative 1 wherever we saw an x, well, I get negative 1 to the 4th power, which is positive 1. Positive 1 times that 2 out front is 2, and 2 plus 9 is 11. So I have 11 in my numerator, all over -1 cubed is -1. So this would give me back -11. So when x is -1, I have -11. I have a point right in here, which tells me then, because of the odd function, then 111 must also be a point. So I know I also have a point up here at 111. So So knowing where my asymptotes are, I know I'm going to be getting closer and closer to my vertical asymptote on the left-hand side and the right-hand side of the graph. I'm going to turn around somewhere, I'm not sure where, because I'm not going to cross the x-axis, and then I'm going to start following and hugging this line y equals 2 to the x. This is a mirror image. So I have the same thing above here. And so knowing again where our asymptotes are and plotting a couple points, we can see and get a general idea what our graph looks like. Again, won't know where it's turning around direction, where my local max or local mins will be in this case. But once you have tools of calculus, you'll be able to find those values. So there's one other thing that I might ask you if you were taking a test in my class. I might ask you, does our graph of f of x cross that oblique asymptote? Or if it was a horizontal asymptote, I might ask you, does it cross the horizontal asymptote? We'll never again cross a vertical asymptote. And so in this case, if I wanted to see if f of x was crossing the line y equals 2 to the x, that was our oblique asymptote. So I'm going to want to know, does h of x ever equal my value y? Does my h of x function 2x plus 9 over x cubed, does that ever equal my y, which was 2x? And so we want to go in here and we want to solve for x. I would probably start by clearing my fraction and multiplying both sides by x cubed. Or actually, just because I see it, let's do this first. Notice if we subtract 2x on both sides of our equation, well, 2x minus 2x cancels on the left, and 2x minus 2x cancels on the right. And so you're left with 9 over x cubed equals 0. Now, if we multiply both sides by x cubed, I get 9 is equal to 0. This is a false statement. So if you get some false statement like this, it tells you that it's not going to cross. So false. The graph does not cross the oblique asymptote.